Hi everyone, it's Rose, and let's start with part 2 of the lecture, which will be about genotypic values. Now I'd like to start with a key message from the previous slides, and that is that quantitative traits are often defined by many different genes, and each gene contributes to the phenotypic variation with a small effect. And typically these effects are additive. Now let's take a closer look at what this additive effect means. So what we have in this illustration, we see a typical additive effect. On the top we have the genotypes A1A1, A1A2, and A2A2. On the bottom we have the genotypic value, which can be, when you're in the middle, it's 0, and then if you have A1A1 it's minus A, and if you have A2A2 it's plus A. And when you look at the plants below, you can nicely see that if you're A1A1 genotype, you're small. If you're A2A2, you're big. And if you're A1A2, you're right in the middle. Now, this is a perfect example of an additive effect. However, what we often see is this dominance effect, like in overdominance, complete dominance, or partial dominance. And this means that the heterozygote is not actually in the middle. It is somewhere closer to one of the homozygotes. Now this overview shows you what kind of situations you can have, like when A1, A2 lies exactly in the middle, your dominance effect is 0 because it's an additive genetic effect. However, when you have complete dominance, meaning that the A1, A2 genotype has exactly the same phenotype as the A2, A2 genotype, your dominance effect will be identical to your additive effect. And you can also have incomplete dominance, meaning that's actually the case that we see it here at the top, where D is somewhere between 0 and A. And then, of course, there is the overdominance, meaning that the heterozygotes perform better than the homozygotes. And that means that D is actually bigger than A. And then there is the effect of underdominance. And that means that the heterozygotes perform less well than the homozygotes. And that would mean that it's smaller than minus A. Okay, so let's take a look at a graph of what it looks like. So on the y-axis we have the genotypic value, and on the x-axis we have the genotypes. And here you can nicely see additive effect, it's a straight line. The moment there's a dominance effect, we see that the genotypic value of the heterozygotes is higher than expected if it was just additive. When we have overdominance, you can nicely see that the genotypic value of the heterozygotes is higher than any of the homozygotes. Okay, so let's do some calculations with these additive genetic values and genotypic values and blah blah blah. Okay, so here right on the right here we have these very morbidly looking mice, which I pretend were trained to lay very still. I called them Frank and Stein. And what we have here is we have this allele, which is the pygmy mutation. And the pygmy mutation occurs randomly, and it results in very tiny mice when they're homozygote for the pygmy mutation. And you can nicely see that the mice on the right, it's very tiny. So it's almost completely recessive, meaning that when you're heterozygote, you're a little bit smaller than the homozygote for the wild type. But it's only when you're homozygote for the recessive that you're really tiny. So these are the observations that we made. And now comes the question. What will be A, so that's the genotypic value, and will be D, the dominance effect? So the first thing we have to do is we have to define that middle point. What is the average of the two homozygotes? So that will be 14 plus 6, because it's the average weight of the wild type genotype is 14. The average weight of the homozygote recessive is 6. And then we see, okay, so 10 is in the middle. And then what we do is we look at the difference between the homozygotes and the average. And that is 4. So that means that our A in this case is 4. And then what is our D? Because we see if 10 is in the middle, we can nicely see here that the heterozygotes actually, they're not 10, they're 12. So there is a dominance effect, meaning that if you have a plus allele, it actually does make you a little bit bigger. And then we see that it's just 12 minus 10, 2. So our dominance effect is 2. So now let's try it yourself with the second example. This one is about sheep. We have this sheep here on the right with a lovely hairdo, and he has wool. We have measurements on wool size. No clue what this means. And I have no clue what the units are here, but for the homozygotes, for the big B allele, they have a wool size of 2.66, and the heterozygotes have 2.17, and the homozygote recessives have 1.48. And now my question to you is this an additive locus, or is there a dominance effect? And what I'll ask you now is to pause this video and to calculate it like we did in the first example. And then go and then play again, and then you'll hear the explanation in the next slide. Okay, so here is the answer. We start by calculating that middle between the two homozygotes. And in this case, that is 2.66 plus 1.48 divided by 2, 2.07. This is the middle. If this middle is the same as the heterozygotes, it would be a purely additive locus. But what we see is that the heterozygotes have an average of 2.17, which is bigger than this midpoint. And that means that it is not additive because it's actually a little bit higher. And now the question, of course, is what is the additive effect of the big B allele? Again, pause the video, calculate it, and then go to the next. Okay, so I hope you paused your video. Let's take a look. So what we do is to calculate the additive genetic effect of the big B allele, we take the wool size of the genotype big B, and we subtract the median point. And that is 2.66 minus 2.07 is 0.59. So the additive effect of the big B allele is 0.59. Now the automatic next question is, what is the dominance effect that we are dealing with here? Again, pause your video and then go to the next slide. Okay, so we calculated a midpoint of 2.07, an additive genetic effect of 0.59 for the big B allele, and now we want to know what is the dominance effect of the big B allele. And that is simply looking at the performance of the heterozygotes, subtract the midpoint. And that is 2.17 minus 2.07 is equal to 0.10. So the dominance effect that we have here is 0.10. Now the key message that I want you to take home from this part 2 of the lecture is that variation in quantitative traits is often determined by many different loci, and each of them have a small effect. And when I say small effect, what do I mean by this effect? I mean that, like you see here below, you see 6 loci, and each locus has their own dominance effect and their own additive genetic effect. So this, and it's all these different loci that eventually determine your phenotype. Like in height, 700 of these loci with 700 different dominance and additive genetic effects, and they determine that variation that we see in height in humans. Now, thank goodness there are some incredibly bright people out there who have developed statistical models to capture this dominance and additive genetic effect and to actually make it useful for calculations. Luckily for you, you're not going to be doing that. Also, luckily for me, because I'm not the biggest fan of it. But in the next couple of slides, we're going to be talking more about this variation and about how we can use it to do some nice algebra and understand genetics better.